In this lecture, we will be discussing addition reactions. More importantly, addition to carbon-carbon double bonds. Right? So, in general, we can say that addition reactions are those reactions where two molecules, right? Suppose say A, Y, and Z is a small molecule here, and here is a carbon-carbon double bond is present. It gives rise to yield a single molecule of the product is called addition reactions. So here the product will look like this one. So this is our addition product, right? And we call these kind of reactions as addition reactions. Here this one pi bond, let me put it like this, say this is our pi bond, right? And this is one of the sigma bonds here, right? So sigma bond, okay. Now these two bonds are broken, right? They are broken. And what is being formed? See, these are the two new bonds that are formed, right? So these two are the two new sigma bonds that are formed, right? Now see, the bonds that are broken is one of them is pi and one of them is sigma, and the two that are formed are both are sigma bonds. So the energy, we know that energy of formation of sigma bonds are much higher than that of pi bonds because sigma bonds are stronger. So in the product, going from reactants to product, we are forming the products which are much lower in energy. That means now we have two more stable sigma bonds in place of one sigma bond and one pi bond. Now therefore these kind of reactions are usually exothermic, right? Right, that means heat is being liberated. Okay, now there can be a lot of addition reactions. We will not go into details of all of them. We will limit our discussion to three main important things, right? Suppose we have this alkene here. So one of them we'll mostly discuss is addition of hydrogen halides, right? And then addition of water itself, and another one addition of halogen molecule as a whole, right? So they will give rise to alkyl halides, right, respectively, we can say. So these are alkyl halides. Then you can get alcohol from addition of water, and we can get dihalides, vicinal dihalides, right? Sorry, vicinal means in the vicinity. So there are halogen atoms in carbon atoms which are side by side. Now in all these reactions, you see that they are similar. This one pi bond is broken and one sigma bond is broken between the molecule that is adding, and we are forming two new sigma bonds. These kind of additions are called electrophilic additions. Why they are called electrophilic additions? See, in both eliminations and these substitution reactions that we have studied in previous lectures, we saw that we saw that the electron pair that is used for bond formation is supplied by the bases, right? Suppose we have used in substitution, say, so in substitution reactions, what we have used? We have used, say, sometimes the chloride, or that means the halide ions, or even the a bit strong bases as the electron pair donor. Like we have used sodium ethoxide also, right? So these are our electron pair donor, right, for the bond formation that is taking place in substitution reaction. Or there are neutral nucleophiles also, right? Now these were also used in elimination reactions, right? So in both in substitution and elimination reactions, the electron pair that was donated was for bond formation was either done by the nucleophiles or the bases that were used, right? But in addition reactions, we will see that the electrons necessary for formation of this new bonds are actually donated from this one of the pi bonds that is broken, right? So here we can say that the electrons of the pi bond, right, or the alkene itself is acting as the nucleophile. Now, before going into details discussion of electrophilic addition reactions to our double bonds, right, let us first discuss the structure of the double bond itself, right? So if you remember that these carbon-carbon double bonds, right, so they are this structure around the carbon-carbon double bonds are planar, right? Now, as I have drawn this molecule here, you can see there's these two bonds, the solid bonds are pointing towards us, and suppose these dotted bonds are away from us. That means we have kept this planar molecule in a plane that is perpendicular to the screen, right? And these carbons are sp2 hybridized, right? Now, how are these pi bonds formed, right? They are formed by direct overlap of the unhybridized p orbitals that are lying perpendicular to the plane of the molecule. So these orbitals are actually perpendicular to the plane of the molecule, right? So you can see clearly that if we say that the yellow parallelogram is the plane for the molecule, right, and these are perpendicular to it, the pi orbitals are perpendicular to it. So the pi bonds that are formed, right, will be what? Will have electron density that are above and below the plane, okay? So that are above and below the plane. As such, they are much more exposed than the sigma bonds, and any electrophile, right, we can donate electrophile which say like this E, right? Any electrophile when it approaches in the vicinity of this molecule, right, they are attracted by the electron cloud, pi electron cloud of these pi bonds, right? Now let us consider each cases one by one. Now, firstly, we will discuss the addition of hydrogen halides to carbon-carbon double bonds. Right. Now, bearing in mind the nature of the strength of these hydrogen halide bonds, right, we can easily say the rate of the reactions or the order of reactivity is like this, right? Then HCl and then lastly HF. That means Hi is most reactive to this reaction and HF is the least. In fact, up to HBr only it is of any synthetic purpose. From HCl onwards, the reactions are so slow that they are of not very much importance. So in the examples we will study, we will use either Hi or HBr. Okay. Now first let us see the mechanism of the reactions, right? Again, this is a multi-step reaction with a formation of carbocation intermediate. So in step 1, we have this pi electron cloud approaching the electrophilic center of this addendum, right? See, due to the polarity of this HX bond, this X end always tends to have a delta negative charge with the hydrogen with a delta positive charge. Now these pi electrons of the pi bond attacks the H end or the positive end of this molecule that is being added, right? And the bond between them, the pair of the electrons that forms the bond between them is pushed towards the X atom, right? Forming the halide ion. So as a result, we have, okay, so we have a carbocation here, right? And so hydrogen is bonded here and we have the halide ion. Okay, so this is our carbocation intermediate. So as in the case of substitution and in elimination where we have carbocation intermediates, this step is a slow step because it involves breaking of a sigma bond. Okay, and in step 2, this carbocation, right, unites with the halide ion, right, to form our product. So form our alkyl halide. So this is fast again, and from our discussions of substitution and elimination, you can now easily visualize how the free energy diagram will look like, right? So reaction coordinates along the x-axis, the reactants will be here, and so a carbocation intermediate is here, so it will always have a double hump type of structure with two transition state and an intermediate. So here intermediate is the carbocation, right, with the hydrogen, and here we have the alkene along with the halide. So here one of the transition state is the approach of the hydrogen halide molecule towards this pi bond. Now once this carbocation is formed, right, the second step also have an transition state. Now this is what the approach of the halide ion or the formation of the bond being formed with the carbocation and the halide ion. So it is something like this, okay, giving rise to our desired product, that is alkyl halide. So what is the delta G of the reaction? So this is the delta G0 for the reaction itself, okay, and the activation energy for the first step for the formation of carbocation, the activation energy is this one, right? So you can say it's like del G1 for the transition state 1, right, TS1. And for the second transition state, what is the activation energy? This is very small because now it is starting from the intermediate itself, so it is very small, this one, right? So this is the activation energy for the transition state 2. So this reaction is very fast, and this one, as the activation energy is very high, this is slow. So till now we have used only a general example like only a carbon-carbon double bond. We have not shown anything in the substitutes, right? So if you take, it's an ethene, right? Ethene, right? And if you add, say, HBr, what you will have? You will have this one, ethyl bromide, right? Now if you have, so there is no confusion here, okay? Again, if you have in place of, say, ethene, if you have 2 butene, right, you can have 2 butene also here. And if you say do the same reactions, electrophilic addition of HBr to it, again you will have this. So you will have 2 bromobutene, right? And Br here, okay? Here also you do not have any other possibility of formation of any other product, right? Of course you have a chiral center now. This is a chiral center, and we'll come to this case specifically later, right? The addition of HBr to bromobutene, right? So there is possibility of formation of R and S, but that we'll discuss later, right? But you see, there is no other formation of any other product. That means you cannot form one butane or something like that, right? But if you have now, say, propene, right? Now if you have propene now and do the same reaction, now there is possibility of 2 products, isn't it? Now the bromine can add in the number 1 carbon atom, or it can add to the number 2 carbon atom also, okay? So you can have either this product, or you can have right. Now the question arises, which one will form, right? Now to answer this question, we have to revisit our mechanism, right? Suppose now we start with propane, okay? So we have CH3 here and H here, and we subject to this hydrogen bromide. Now due to polarity, we have delta minus here and delta plus here. In the step 1, what happens? These approaches here. See, so if you write it here, step 1, in step 1 only there are 2 possibilities, right? This bond can open up this side to form the carbocation on the carbon number 1, or it can also open this side to form the bond on this carbon number 2, right? So there are 2 possibilities. So let's see one by one, okay? So this yellow arrow is for this pathway, okay? So if the carbocation is formed as per that is shown by the yellow arrow, then we'll have, and the hydrogen will add here because the electron pair is on the number 1 carbon atom now, okay? And if it follows the path that is shown by the red one, then we'll have this hydrogen. Now hydrogen will add up here, and we'll have the carbocation in this place, okay? See, so to demark it, let me say we have this blue hydrogen for hydrogen bromide, then these hydrogens are from the hydrogen bromide, okay? Now you see there are 2 types of carbocation here, right? This is what? This is a secondary carbocation or 2-degree carbocation, right? whereas this is a primary carbocation or 1 degree carbocation. Now we know from the stabilities of carbocation that this second degree is much more stable than the primary carbocation. As such, the reaction will always take this path and rather do not follow this path to form the unstable carbocation. It will not follow. Right? So this intermediate will never be formed. As such, the product will only follow from here and will get what? Will get CH3, this product, right? We'll get only this product, right? Sorry, yeah. So that is 2-bromopropane. Okay. Now these results are usually stated in a general form by what is called Markov-Nikov's rule, right? So what does Markov-Nikov rule say? That the positive part of the addendum, it says that a positive part of the addendum will add to an unsymmetric double bond in such a way that this positive part adds to the carbon atom that bears the highest number of hydrogen. See, in this the example we took of these two carbon atoms, this is the carbon atom that has higher number of hydrogen, right? And this hydrogen has attached here. So we have this product, right? So we have already known the statement of Markov-Nikov rule for a long time, right? Now you see the basis of this Markov-Nikov rule is the mechanism that is following via carbocation mechanism, right? These kind of reactions that we have just seen, that is the Markov-Nikov rule, are called regioselective reactions, right? Why regioselective? Because whenever there is possibility of formation of two types of constitutional isomers like 2-bromopropane or 1-bromopropane, and one is favored in expense of the other, right? So in one regional isomer is favored. So these kind of reactions are called regioselective reactions, when only one of the constitutional isomer is favored over the other. Now if you subject the same 1-propene, right, to addition of HBr, but this time in the presence of a organic peroxide, right, you will end up having the anti-Markov-Nikov product, that is our 1-bromopropane, right? Why this is formed? To answer this question, we again have to visit the mechanism of this reaction in presence of peroxide. So in presence of peroxide, it is again a multi-step reaction. So in step 1, right, this is the peroxide, right? So whenever you heat it, produces this homolytic cleavage, right? Homolytic cleavage means one electron is shared by each of the atoms that are bonded. So it produces this radical ion. Okay, so now this oxygen have an unpaired electron. So this is the radical, or generally what we call free radical. Okay, and these are very reactive species. Now in step 2, this free radical, right, reacts with the HBr molecule to form now bromine free radical. Okay, so now bromine free radical is formed. along with the alcohol. In the next step, this bromine free radical reacts with our substrate, that is this, say, CH2 double bond CH and CH3. So it reacts with the propene, okay, to generate another free radical. So we have CH2Br bond. So now the free radical is on carbon, right? So this is again a 2-degree free radical, right? And in step 4, this free radical, that means the 2-degree free radical, reacts with another molecule of HBr. Similarly, in step 2, they produce another free radical of bromine free radical, right, which is used in the next step for propagation of the reaction and our product, that is anti-Markovnikov product. So we have CH2Br, CH2, CH3, right? So one bromopropane. So this is exactly opposite that we got from Markovnikov addition. Now see, in step 3, this is our important, right? Important step. This is what is concerned in this mechanism. In step 3, there are again 2 types of possibilities to form this free radical, right? If the bromine would have attached in this carbon atom, right, then what would have happened? This would have led to the formation of a free radical that would look like this one. Now this is 1 degree, right, free radical. This is unstable, so this will not form. Whereas only the 2 degrees, the stable possibility, will form and give rise to the product. So this explains why in presence of peroxide, the orientation of the products completely changes from this Markovnikov addition to anti-Markovnikov addition, and this effect is called Kharash peroxide effect, or more generally it is called peroxide effect. Now let us examine the stereochemistry of hydrogen halide addition to alkenes. Now if we take an example of an alkene which can give rise to a chiral product, right, say if we have, say, butene here, right, so if we start with 1 butene, right, then of course there are 2 possibilities of formation of carbocation, right? We can So of course there is 2 possibilities of formation of carbocation. So one is here and one is here. So if you form the carbocation in this carbon, then it will be 2 degree, whereas this will give 1 degree carbocation. So we are not going to see the reaction pathway which gives 1 degree carbocation will form the 2 degree carbocation here. So the 2-degree carbocation, if we write it like this, H, and so the methyl group towards us, we are drawing it like this, right? So it's HBr. Okay. Now this is what? This is planar, and so it is achiral. Okay. Now as this is achiral, next the bromide ion now has the possibility to attack it from both the faces equally, right? It can attack either from up or either from down, right? Because this is achiral and the bromine has no preference. If it looks from upside or downside of the plane, it has no preference to attack from either of the sides. So there is equal possibility of attacking from both the sides, and 50% occurrence reactions will occur from either side, and as a result will end up with products like this one. So in this case, if it attacks from the top, right? So let us say it's beer here, H CH3 and the other isomer will be H5. So now these orientations will be different, right? Now you see these two are mirror image to one another, right? So if you have a mirror here, you see they are as if they are mirror image to one another, right? Just because the attack of the bromide ion from the other faces, different faces, right? So this mirror image relationship between them leads, that means they are enantiomers, right? They are non-superposible mirror image to each other, and we have here in this case, this is the S2 bromo butane, and here we have the R2 bromo butane, right? And what is the ratio? This is 50% and this is 50%. That means we get a racemic mixture, right? That is mixture of two enantiomers in equal proportions. So this kind of addition, that is hydrogen halide, when it adds, does not produce any specific stereoisomers wherever there is a possibility. Rather it produces enantiomeric mixture, right? We get racemic mixture for hydrogen halide, because again, why? Because this follows a carbocation intermediate, and as such there both the attacks from both the ends are equally possible. Now let us discuss the acid catalyzed hydration of alkenes, right? Or simply we can say this is the addition of water across the carbon-carbon double bond. So here what usually is taken is a very dilute solution of a acid like sulfuric acid or phosphoric acid, right? And the end product is our alcohol, right? So this again is the regioselectivity is same as Markov-Nikov rule, right? So the regioselectivity will be according to this Markov-Nikov rule. addition, right? That means the positive part of the addendum will add up to the carbon that has the higher number of hydrogen. So in this case the positive part is the H and the negative part will be the OH, right? So let us take an example of unsymmetric alkene like our propene that we took for HBr addition also. So here what we'll have, if we subject it to acid catalyzed hydrolysis, then we'll end up with, now the positive part will add up here, so it will be the hydrogen will go here and the OH will be added in the 2 carbon atom, so we'll end up getting 2 propanol, right? So this is a 2-degree alcohol or secondary alcohol, right? So by this acid catalyzed hydration of alkenes, we cannot produce a primary alcohol, right? We will always end up with a secondary or 3-degree alcohol as the case may be, but will not end up with a primary alcohol except in the case of ethene, right? In the case of ethene, right, we will end up with ethyl alcohol, a primary alcohol, if we have the same acid catalyzed hydrolysis, right? Okay. Now let's examine the mechanism of this reaction. Now this mechanism is again via carbocation formation, as in the case of addition of HBr or any hydrogen halides, right? So in the step 1 we have the formation of carbocation. So let's take the same example of propene, right? Now we have this H3O plus here, right? So this electron cloud attacks one of these protons and this electron pair goes to neutralize the positive charge on water, giving rise to what? A carbocation. Now which carbocation will form? We know that it will be the secondary carbocation, right? So this secondary carbocation will be the result of this first step, right, along with of course water, right? In step 2, this secondary carbocation that is formed will react with water, right, to form the protonated alcohol. So we have now this protonated alcohol, right? Okay, now in the last step, the protonated alcohol transfer a proton to the water molecule to regenerate the alcohol and the acid catalyst. Okay, so it will be we'll get our secondary alcohol, that is 2-propanol here in this case, and the acid catalyst is regenerated. So the rate determining step is of course step 1, because this involves the formation of a carbocation, right? So this is slow step and this is the rate determining step for this reaction. Now one of the problem with such a mechanism with a carbocation intermediate is that the possibility of rearrangements, right? Suppose you take this alkene, so this is 2,3,3-dimethyl 1-butene. Now if you subject to this to acid hydrolysis, right, so you expect what? The carbocation to form here, right, and you will have a product that is like this. Okay, so you expect 3,3-dimethyl 2-butanol, right? But this is not the product here, right? This is not formed, right? What is formed is rather you have this one. So this is 2,3-dimethyl 2-butanol, right? So why this is formed and why not this one? This is the expected, right? This is the expected product, but we get this one. See, once you form the carbocation, stable carbocation from this, let's start from there, right? So you have from the first step, after the first step you will have this carbocation. So once this carbocation is formed, this is a 2-degree carbocation, right? Now here are 3 methyl groups also, right? You see, in the stability of carbocations we know that 3-degree carbocation is more stable than 2-degree carbocation. Now see, if one of the methyl group is shifted to this carbon atom, then there is a possibility of forming more stable carbocation. See, if that methyl group shifts to the adjacent carbon atom where the charge actually belong, then you have this carbocation, right? This is now a 3-degree carbocation which is more stable than the 2-degree carbocation. Now in the second step, so this rearrangement is very fast, and as soon as this carbocation is formed, then only the rearrangement takes place to form the more stable 3-degree carbocation. And as the 3-degree carbocation is formed now in the solution, then the water reacts with this 3-degree carbocation to give the product that is obtained, right? Not the product that is expected. So this is one of the complications of this acid catalyzed hydrolysis. To overcome this, we can use other reagents like mercuric acetate and all that. So oxymercuration, demercuration, which gives exclusively Markovnikov type of addition. But we will not consider these discussions here. We will now next move on to addition of halogens. So we all have learned from school level that bromine water can be used as a test for unsaturation, right? The red color of bromine water is decolorized by alkenes. So this is nothing but a case of addition of halogen to alkenes that we will study now. Now we have to know the mechanism for it, right? So this is again a multi-step reaction. In step 1, there is a formation of cyclic bromonium ion, right? So say you have, right, so you have an alkene like this, so which is perpendicular to the plane of the screen that you are viewing, right? And suppose the bromine molecule, so Br2 is approaching it, the coming near the pi bond, right? Now as such, this pi electrons pushes the electron of the bromine atom which is nearby towards this bond, right? And thereby what happens is it have a delta positive charge, and here this one have a delta negative charge. And as such, this bromine atom now becomes electrophilic, and a bond is formed from the carbon bromine bond, right? Now this carbon atom can become a carbocation, right? But due to the presence of these lone pairs, it actually forms a bond, another bond. This bromine forms another bond with the other carbon atom, right? So giving rise to what is called is this cyclic bromonium ion, right? And there is a change in the orientation of the other bonds, because now bromine is in this half. So this is our cyclic bromonium ion, with two lone pairs and a positive charge is there, okay, and plus you have the bromide ion, okay. Now you see this is the cyclic bromonium ion. Now the next step is the attack of the bromine, this bromide ion, into this cyclic bromonium ion to form the dibromide. Now you see this bromide ion cannot attack from this side, right, because this is hindered by the large bromine ion itself, right. So this is hindered here, so it cannot attack from this side. So what it will do, it will obviously attack from the other side, and as you can see there are equal possibilities of attacking either of the carbon, right. So there is 50% attack on both of the side, right, giving rise to enantiomers. So this is the step 2. So step 2 will look like, suppose I am drawing in say if it attacks here, so this will give rise to this kind of product. See, it will be then, so this solid bond, these bonds will be like this, the bromine will come up here, right, and you have and bromine. So this is from this yellow arrow, okay. So I mark it, circle it like yellow. Now if the other path is followed, say this bromine now attack this carbon atom, and now this bond will open up. So what we will get, this time you will get, so the bromine now will be here, right, the incoming bromide ion, and so let me circle it like this is from the blue arrow mechanism, right. Now you see what is the relation between these two. They are mirror image, non-superimposable mirror image relationship, right. That means they are enantiomers, right. So in this cyclic bromonium mechanism you will end up with enantiomers, as with the case of carbocations, right. Now more interesting is the stereochemistry of this bromine addition to cis and transalkene. We have taken here, you see, the examples of cis butene, 2-butene and trans 2-butene. Let's see if they yield the similar products or not, right. Now if you subject them to this bromine addition, right, so what is the first step? In the first step, in both cases we will have the cyclic bromonium ion, right. So let us draw this cyclic bromonium ion, right. So in this case, this for the case of cis, it will look like this. So both the CH3s will be towards us, right, and both the hydrogens will be away from us. So this is the cyclic bromonium ion here. And in the case of the trans one, we will have one of the methyl groups, that is it will be away from us, and the other methyl group will be towards us, okay. Now again we have to have two kinds of attack, right. So here in the second step, the bromide ion in the first case, see, can attack here and can also attack here, right. In two cases we will have different kinds of products, right. So let's say the yellow one be the A and the blue one be the B product. So what we will get from the A one, we will get bromine, so methyl hydrogen, and this opens up here, so bromine will be here and this will be similar, right? Sorry, 3. Okay, and we'll get so this is from A, right? And we'll get another product from the pathway of B, right? So in this case the bromine will be here, CH3H, and this bromine will be here. So this is from B. Okay, so now you see what is the relation between them. These are again non-superimposable mirror image relationship, isn't it? See, so they are enantiomers, right? Right, and obviously this is the you can easily work it out. I'm just writing it down. This is the RR and this is the SS. Okay. Yeah, so you get a 50% mixtures of this SS isomer and the 50% of RR isomer, giving rise to a racemic mixture, right? Now let us see the other case, that is from transbutene, right? So here also there is two possibilities and we mark it similarly, like this one be our A, the pathway A, and let this be our pathway B, right? See what we get here. From the pathway A, we will get here bromine, so hydrogen is here, methyl hydrogen, and the bromine will be here. Now the methyl in this case will be in front of us and hydrogen will be back. Okay, so this is from A, and similarly we will get another product from the B pathway. So here bromine, methyl hydrogen, and the bromine will be here now, hydrogen in the front, methyl at the back. See, you can say that these are again mirror images, right? But these are not non-superimposable, these are superposable. Suppose if you just rotate it, suppose there is an axis, if you rotate it 180 degree, then you end up here. You see, these are same, right? They are same type of compound, they are not different compounds, right? So actually what then what are they? They are not enantiomers, but they are, this is the mesoisomer, right? Or the RS, right? As we have seen. So you can easily see it. Suppose if you rotate any one of them will do. If you rotate it, this carbon atom, the bonds, right? So that you can end up here, say in the, it will look like this, bromine, and so that you have in eclipsed form, then what you have? You will have this methyl is here, hydrogen, methyl will be here, and the hydrogen will go back, right? If you just rotate it, that means now you see there is a plane of symmetry along this bond, mid of this bond, right? They are reflected on each other in this eclipsed form, right? That means this is a meso compound. So what you have got, so the important thing about addition of bromine and in cis and trans alkane is, see, when you start with the trans isomer you end up with meso, and when you start with cis isomer you end up with enantiomers, pair of enantiomers, right? So these kind of reactions where a particular stereoisomer of the starting material yields a specific stereospecific form of the product are called stereospecific reactions, right? These additions are therefore stereospecific. Right, because when you start with cis you end up with two different compounds. When you start with trans you end up with another form, right? So whenever there is this kind of reaction is there, that a particular stereoisomer of the starting material yields a specific stereoisomer of form of the product, then these kind of reactions are called stereospecific reactions.